Hello friends, welcome to this YouTube channel. Today we are going to solve a couple of numerical problems on resistance. By solving these problems, we shall learn how to compute resistance of a conductor when values of length and cross-sectional area of the conductor and resistivity of the material are known. When temperature remains unchanged, the resistance of a conductor is directly proportional to its length, that is, R is proportional to L. It is inversely proportional to its area of cross section, that is, R is inversely proportional to A, and it depends upon the nature of material. Now we can write R is proportional to L by A. Therefore, R equals to rho into L by A, where proportionality constant rho is termed as resistivity of the material or specific resistance. When L equals to 1 meter and A equals to 1 square meter, R equals to rho. Hence, specific resistance or resistivity of a material is the resistance offered by 1 meter length of wire having an area of cross-section of 1 square meter. Reciprocal of resistance is termed as conductance. G equals to 1 upon R, that is equal to 1 upon rho into A by L. This may be written as sigma into A by L, where reciprocal of resistivity sigma is termed as conductivity. We have to calculate the resistance of a 75 meter length of wire having a uniform cross-sectional area of 0.3 square millimeter if the wire is made of material having a resistivity of 90 microohm centimeter. Let us first write down the given data. Length of wire L equals to 75 meters. Cross-sectional area A equals to 0.3 square millimeter, that is equal to 0.3 into 10 to the power minus 6 square meter. Resistivity of the material rho equals to 90 microohm centimeter, that is equal to 90 into 10 to the power minus 8 ohm meter. Let us now calculate resistance of the wire. R equals to rho into L by A. Using values we get 90 into 10 to the power minus 8 into 75 divided by 0.3 into 10 to the power minus 6. That gives us 225 ohm. A cube has resistivity of its material as 20 microohm centimeters. If it has all sides of length 5 centimeters each, we have to calculate the resistance of the cube between any two faces. Let us first write down the given data. Resistivity of the material rho equals to 20 microohm centimeters, that is equal to 20 into 10 to the power minus 8 ohm meter. Dimensions of the cube. Side x equals to 5 centimeters, that is equal to 0.05 meter. Length L equals to x, that is equal to 0.05 meter. Let us now calculate cross-sectional area. A equals to x into x, that is equal to 5 into 5 that gives us 25 square centimeters or 25 into 10 to the power minus 4 square meter. Resistance between any two faces R equals to rho into L by A. Using values we get 20 into 10 to the power minus 8 into 0.05 divided by 25 into 10 to the power minus 4. That gives us 4 into 10 to the power minus 6 ohm or 4 micro ohms. A rectangular bus bar is made of aluminium and is 100 cm long, 10 cm wide and 2 cm thick. If the bus bar current flows along its length, we have to calculate the bus bar conductance provided the bus bar conductivity is 360 megamho per meter. Let us first write down the given data. Conductivity of aluminium sigma equals to 360 megamho per meter or 360 into 10 to the power 6 mho per meter. Dimensions of the bus bar. Length L equals to 100 centimeters, that is equal to 1 meter. Width W equals to 10 centimeters, that is equal to 0.1 meter. Thickness T equals to 2 centimeters. When current flows along the length of the bus bar, cross-sectional area A equals to W into T, that is equal to 10 into 2, that gives us 20 square centimeters or 20 into 10 to the power minus 4 square meter. Conductance between opposite ends G equals to sigma into A by L. Using values we get 360 into 10 to the power 6 into 20 into 10 to the power minus 4 divided by 1. That gives us 0.72 into 10 to the power 6 mho or 0.72 mega mho. We have to calculate the resistance of a copper tube having outer diameter 8 centimeters, thickness 5 millimeters and length 5 meters. Given resistivity of copper is 1.7 micro ohm centimeter. Let us now write down the given data. Resistivity of copper rho equals to 1.7 micro ohm centimeter, that is equal to 1.7 into 10 to the power minus 8 ohm meter. Dimensions of copper tube. Length L equals to 5 meters. Outer diameter capital D equals to 8 centimeters. Thickness T equals to 5 millimeters, that is equal to 0.5 centimeter. Let us now calculate inner diameter. Small d equals to capital D minus 2 times T. Using values we get 8 minus 2 into 0.5, that gives us 7 centimeters. Cross-sectional area A equals to pi by 4 into capital D square minus small d square. Using values we get pi by 4 into 8 square minus 7 square, that gives us 11.781 square centimeters or 11.781 into 10 to the power minus 4 square meter. Let us now calculate resistance of the copper tube R equals to rho into L by A. Using values we get 1.7 into 10 to the power minus 8 into 5 divided by 11.781 into 10 to the power minus 4. That gives us 72.15 into 10 to the power minus 6 ohm or 72.15 micro ohm. We have to determine the resistance of a coil of mean diameter 5 centimeters containing 500 tons of manganese wire 0.05 centimeter in diameter. The resistivity of manganese is 42 micro ohm centimeters. Let us first write down the given data. Resistivity of manganese rho equals to 42 micro ohm centimeters, that is equal to 42 into 10 to the power minus 8 ohm meter. Number of turns N equals to 500. Diameter of the coil capital D equals to 5 centimeters, that is equal to 0.05 meter. Diameter of wire cross section small d equals to 0.05 centimeter. Let us first calculate length of one turn. L1 equals to pi times capital D, that is equal to 0.05 times pi meter. Length of the wire L equals to N into L1. Using values we get 500 into 0.05 times pi, that gives us 25 times pi meter. Now we shall determine cross-sectional area. A equals to pi by 4 into small d square, that is equal to pi by 4 into 0.05 square. That gives us 625 times pi into 10 to the power minus 6 square centimeter or 625 times pi into 10 to the power minus 10 square meter. Expression for resistance of the coil R equals to rho into L by A. Using values we get 42 into 10 to the power minus 8 into 25 times pi divided by 625 times pi into 10 to the power minus 10. That gives us 168 ohm. A coil comprises of 2000 turns of copper wire having a cross-sectional area of 1 square millimeter. The mean length per turn is 75 centimeters and the resistivity of copper is 0.02 micro ohm meter. We have to calculate the resistance of the coil and power absorbed by the coil when connected across 180 volt DC supply. Let us now write down the given data. Supply voltage V equals to 180 volts. Resistivity of copper rho equals to 0.02 micro ohm meter or 0.02 into 10 to the power minus 6 ohm meter. Number of turns N equals to 2000. Cross-sectional area A equals to 1 square millimeter, that is equal to 1 into 10 to the power minus 6 square meter. Length of one turn L1 equals to 75 centimeters, that is equal to 0.75 meter. Let us now calculate length of the wire. L equals to N into L1, that is equal to 2000 into 0.75, that gives us 1500 meters. Expression for resistance of the coil R equals to rho into L by A. Using values we get 0.02 into 10 to the power minus 6 into 1500 divided by 1 into 10 to the power minus 6. That gives us 30 ohm. We shall now determine power absorbed by the coil. P equals to V square by R. Using values we get 180 square divided by 30. That gives us 1080 watts. A rectangular copper strip is 20 cm long, 1 cm wide and 0.4 cm thick. Taking resistivity of copper to be 1.7 micro-ohm centimeter, we have to calculate the resistance between opposite ends and opposite sides. Let us first write down the given data. Resistivity of copper rho equals to 1.7 micro-ohm centimeter, that is equal to 1.7 into 10 to the power minus 8 ohm meter. Dimensions of copper strip. Length L equals to 20 centimeters, that is equal to 0.2 meter. Width W equals to 1 centimeter, that is equal to 0.01 meter. Thickness T equals to 0.4 centimeter. When current flows between opposite ends, cross-sectional area A1 equals to W into T. Using values we get 1 into 0.4, that gives us 0.4 square centimeter or 0.4 into 10 to the power minus 4 square meter. Let us now calculate resistance between opposite ends. R1 equals to rho into L by A1. Using values we get 1.7 into 10 to the power minus 8 into 0.2 divided by 0.4 into 10 to the power minus 4. That gives us 85 into 10 to the power minus 6 ohm or 85 micro ohm. When current flows between opposite sides, cross-sectional area A2 equals to L into T. Using values we get 0.2 into 0.4, that gives us 0.08 square centimeter or 8 into 10 to the power minus 6 square meter. Resistance between opposite sides. R2 equals to rho into W by A2. Using values we get 1.7 into 10 to the power minus 8 into 0.01 divided by 8 into 10 to the power minus 6. That gives us 0.2125 into 10 to the power minus 6 ohm or 0.2125 micro ohm. A transmission line cable comprises of 19 strands of identical copper conductors, each 1.5 millimeter in diameter. The length of the cable is 4 kilometers, but because of the twist of the strands, the actual length of each conductor is increased by 5%. Taking the resistivity of copper to be 1.78 micro-ohm centimeter, we have to calculate the resistance of the cable. Let us first write down the given data. Resistivity of copper rho equals to 1.78 micro-ohm centimeter, that is equal to 1.78 into 10 to the power minus 8 ohm meter. Length of the conductor L1 equals to 4 kilometers. Diameter of conductor cross section small d equals to 1.5 millimeter. Number of strands N equals to 19. Let us first calculate cross-sectional area of the conductor. A1 equals to pi d square by 4, that is equal to pi by 4 into 1.5 square, that gives us 0.5625 times pi square millimeter. Net cross-sectional area A equals to n times A1, that is equal to 19 into 0.5625 times pi, that gives us 10.6875 times pi square millimeter, or 10.6875 times pi into 10 to the power minus 6 square meter. According to the problem statement, because of the twist of the strands, the actual length of each conductor is increased by 5%. Therefore, actual length of conductor L equals to 1 plus 5 by 100 into L1, that is equal to 1.05 into 4, that gives us 4.2 kilometer or 4200 meters. Let us now determine resistance of the cable. R equals to rho into L by A. Using values we get 1.78 into 10 to the power minus 8 into 4200 divided by 10.6875 times pi into 10 to the power minus 6, that gives us 2.2266 ohm. A rectangular metal strip has the dimensions x equals to 10 centimeters, y equals to 2 centimeters, and z equals to 1 centimeter. We have to determine the ratio of the resistances Rx, Ry and Rz between the respective pairs of opposite faces. Let us first write down the given data. Dimensions of metal strip. Length x equals to 10 centimeters, width z equals to 1 centimeter, and thickness y equals to 2 centimeters. We know that expression for resistance R equals to rho into L by A. When current flows along x-axis, resistance Rx equals to rho into x by yz. When current flows along y-axis, resistance Ry equals to rho into y divided by zx. When current flows along z-axis, resistance Rz equals to rho into z divided by xy. Ratio of resistances Rx is to Ry is to Rz equals to rho into x by yz is to rho into y by zx is to rho into z by xy. This may be written as x by yz is to y by zx is to z by xy. Using values we get 10 by 2 into 1 is to 2 by 1 into 10 is to 1 by 10 into 2. That gives us 100 is to 4 is to 1. So today we have solved a couple of numerical problems on resistance. By solving these problems, we have learned how to compute resistance of a conductor when values of length and cross-sectional area of the conductor and resistivity of the material are known. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.